Now we shall be looking at the energy associated with self-induction, right? So energy associated with self-induction. Now, as we know, in a self-induction, this is a circuit right, and over here some I shall flow the current. This will be the I. This is the positive side of this battery, this is the negative side. Now, to understand this energy associated with self-induction, we have to understand the work done, right? Now, what is the work done? See, over here the I will be a time varying, right? Because whenever we will make or break this circuit, this I will become time varying, right? And we know the formula that an opposing EMF that will be produced or induced due to the self-induction, the formula is as such: E is equals to minus L, where L is the coefficient of self-induction, or it is also known as self-inductance, right? L multiplied by the rate of change of I. Okay, we know it from the previous lectures. Now let us check the work done. A small amount of work done in this circuit, right? In order so that an opposing EMF will be produced due to this current flowing for a specific small interval of time dt. So it will be the EMF multiplied by the current and multiplied by the time change, right? So now we can write this dW as equals to minus of E. Why? Because the actual EMF was in this direction, say for example, and the EMF now induced will be in the opposite direction such that it will oppose the change which is producing it from the Lenz's law. So we have to take it minus of this E multiplied by this current I multiplied by the small change of this dt, right? Over here, this term of E, it could be replaced by this one, right? So what we will get? This negative will now be positive term. L I for this one multiplied by this term d by dt component of I for the time interval t. A small time interval has been taken out, and for that small interval of time we wish to find out the work done. So these dW will now be equals to Li di, right? Now for the entire work done for the time interval from 0 to t, we wish to find out if the time interval now is from 0 to t, then the current that will rise will from 0 to the highest level, the maximum level of I, as we have seen previously in this kind of diagram, right? And after that this will fall like this. So over here this will be from 0 to t time interval, and over here the attain of the maximum value will be from 0 to I. This is current, and over here we take the time. So for the small interval of time we are taking the small currents now. The small currents would now be equated and they will be integrated over the interval from 0 to I. From 0 to I. Right? Here L is a constant. We can take it outside. Is equals to L integration from 0 to I of I di. Now we know that the integration of I or x dx will be equals to x square by 2. Integration of x dx will be equals to x square divided by 2 to the limits of say 0 and c, right? Over here we could write it as W equals to L multiplied by I square divided by 2 from 0 to I, right? So we could find out here that the work done over here is equals to 1 by 2 multiplied by Li squared. Now, this I which has been attained, this is the peak value, right? So we can give it I naught, the peak value, right? So we need to integrate it now to I naught, and if this is I naught, this will be I naught once again, this will be I naught, and hence the formula which we will get will be W equals to half times of the self-inductance multiplied by the square of the peak value of current flowing, right? So this is the work done, and we know that the work done is actually stored as energy. So we could say that the energy associated with self-induction in this scenario will be equals to 1 by 2 half Li naught square, right? Thank you.